For my lab, I observed the motion of rolling a tennis ball on the counter at constant speed. Then I used this video and analyzed it on Tracker, which I compared it to a computational model which I made on Python, as you can see here. My question was whether the predicted model would be similar to the actual model when using the physics principle of Newton's second law. For our results, we found that the experimental model was quite similar to the computational model. On Tracker, I first figured out which frames I wanted to use, which was from 46 to 67. That was because that was the time where the ball was not bouncing, and it eliminated the use of pushing the ball off the book, which would be a net force. And since we were trying to find the constant speed at constant non-zero velocity, we would not try to show that. Okay, after that, I used the calibration stick in order to find the distance that was used in general. Well, I knew that the diameter of a tennis ball is 0.067 meters, so I used that to calibrate the distance that was made. Next, I used the coordinate system in order to align the ball to the origin, mass in order to basically find the average position. This makes sense because there is no net force acting on the ball, which would eliminate the use of F net divided by mass times the change in delta t, and would only leave us with constant velocity, which would also mean that the slope would be approximately continuously the same throughout the graph. Next, I went on to edit the Python file that was given. First, I changed the ball's mass to 0.058 kilograms because that's how much a tennis ball weighs. Then, I changed the initial position vector by figuring out that as the time is 0, the x position would be at 0.004 units. Next, which is in meters. And then I found the ball's initial velocity by using the formula of average velocity equals the change in position divided by the change in time. For that, I received a value of 0.91 meters over second. I knew that the y component and the z component had to be 0 because we were only looking at the x component in the graph. Therefore, the predicted graph would also only look at the x component. Anyways, the delta t had to be a small amount, so that's why I put 0.01. And then I knew that the F net, or the net force, had to be 0, also because there was no other interactions or forces that were happening upon the ball while it was in constant speed. Then I changed the equation to find the velocity by knowing that the velocity is the initial velocity plus the net force divided by the mass times delta t, which is also Newton's second law. And this is always updated to find the final velocity. You might think that initial velocity looks the same as the initial velocity, looks like the final velocity is also initial velocity, but is not, because this is being updated the entire time. Similarly, I did the same to find the new position, which is the initial position plus the ball's velocity times delta t. Then, I did not do anything to the t equals t plus delta t, which meant that as each new starting time occurred, there would be an accumulation of time steps, which would predict the position versus time graph. That's why the final time would keep on updating as the time steps increased, like this. I knew that I had to end at 0.7 seconds because that is where my graph ended. So then I graphed the two, and I saw that there was a slight difference in the slope. This could be because the motion of the tennis ball goes from right to left, as you can see on the video, but it also drifts from front to back a little bit. Since we knew that Newton's second law states that final velocity is found by knowing what the initial velocity is and add that by the net force divided by mass times the change in delta t, we knew that the net force in this case was 0 because there was no other forces acting on it. Therefore, initial velocity would be equivalent to final velocity v, and that also